Okay, so for a while now, I've been very interested in how simple programs run. And one of my favorite classes of programs to look at are rewrite systems because they're extremely intuitive. Um, it really seems to make sense to look at them. So the idea of these systems is that one starts with a string, in this case, a string of red, blue, and green blocks, and one keeps applying rules. So in this case here, for example, the rules are shown at the top. They say replace every red block with two blue blocks, replace blue red with blue green, etc. And what we do to run this system, in this case, we're starting off with two red blocks, and each successive row is a string on a successive time step. So time's basically going downwards. And basically, we just apply these rewrite rules from the left in a kind of non-overlapping way. Now, why this is worth time, why this is interesting, in my opinion, is that what we're getting here from a tiny little rule is this immensely complex pattern growing out. And so it's natural to ask questions like why or what's going to happen. And I don't think anyone really has any concrete answers. It's a phenomenon that's only really been widely acknowledged over the last 10 years, this phenomenon of finding lots and lots of complexity from very simple processes. And I think there's a lot of interesting things to it. So, what I want to do today is just to show you. It's not pre prepared. I just want to have a look at some of these rewrite systems and make some observations and show you, hopefully, how interesting it can be to look around the space of programs. So here we are. The first question we can ask is, what kinds of behavior do we see? So let's make a kind of list of different sorts of behavior. Well, we can start from very simple, okay? This is one of the simplest kinds of behavior we see here on the left. It's what I would call a fixed point. This string here, when we keep updating it, it just ends up not changing at all. Once we get down to one green block, none of these rewrite rules work on one green block, so it just stays the same. Very dull. I'd say the next most interesting thing would be something like this rule in the middle here. It's periodic. I mean, it changes, but every two time steps it comes back to like it was before. So it's a period 2 rule. This one on the right here, this is a period 1, 2, 3, 4 rule. Slightly more interesting, but still nothing to write home about. Now, each of these systems we're starting off with one red block. So let's change that. Let's increase the number of red blocks we start with. What's happening? Okay, so in this particular case, the dynamics aren't getting more interesting. Sometimes in these kind of systems, the period increases, but obviously not today. Well, okay then, so what else can we see? Here is a phenomenon called, well, what I call exponential growth, this thing in the middle here. And again, we've got one of the dullest sorts of versions of it. We'll just start with a couple of red blocks, and then because every red block gets replaced with 2, we just have this exponential increase in number of reds. Again, pretty simple stuff. Now, you can get more interesting kinds of exponential growth. This rule on the left here shows an example. So this has lots of kind of linear patterns running around in it, and it's fairly easy to understand, I guess. But it also has this sort of exponential growth characteristic. So is there anything else we can see? Well, yeah, I think there's... Okay, so here's an example of linear growth. Now this tends to be quite a lot more interesting. this system on the right here. Um, Not always, but often systems which grow linearly can house some very complex dynamics because the system's growing, so you've always got more space for things to happen, but it's not expanding so fast that it's hard for information to move around. So hopefully later we'll see evidence that exponential growth often inhibits really interesting dynamics, but stuff that grows linearly, often it can emulate other systems like cellular automata and things. Anyway, I don't want to talk too much about technicalities about systems which about other things. Let's just have a look at what we have here. Okay, so did you see that? Let's go back to it. We have a rule here which looks pretty interesting. And this is a phenomenon I've only really been noticing quite recently, is that some of these rewrite systems tend to have this property that their complexity seems kind of hidden under a bushel or something. It seems to take a while for it to really express itself. Like, if you look at this system for the first, I don't know, 10, 15 time steps, you probably wouldn't think much is happening. And then somehow on the far right hand side, there seems to be some kind of turbulence or something, which ends up dragging up a really complex pattern. So, as always, the best thing to do to see what's going to happen long term is just to crank up the amount of time this system runs for. Oh, so that's kind of interesting. It turns out that this system is is going into a kind of mode of exponential growth. And it really looks as if this pattern is really highly complex. Does it have any kind of regularity in time? Let's run it for some longer so we can see. Right, so it doesn't even really look as if there's any like this pattern of kind of oh, there we are. Okay, we can see better now. We can see that there is a kind of repeating nature to it. If we draw a line diagonally downwards, we can see parts repeating. Um, and this is often the case when you get this exponential growth. You can get complexity, but it often gets locked into a kind of repetitive growth. So it looks as if this stuff on the far left, these vertical lines, they're perfectly repeating, are they? Yes, it looks as if they're perfectly repeating patterns. So we could essentially just delete all those since we can understand them with finite effort. And then the kind of complex looking stuff looks periodic in time, but in space it seems to be generating ever increasing complexity. So I think this is one of those systems which is kind of out for the jury as far as whether it's comprehensible or not. I'd suggest it probably is understandable, but I think another interesting thing to notice is that there's quite a lot of similarity between this thing on the left and this rule on the right, which immediately looks quite a lot simpler. Let's decrease the time a bit so that we can get a clearer view. So you see this rule on the right here. This is, there's very little complexity going on in time here, but over space, it looks like the way that these strips are distributed is kind of difficult to predict. Like, just looking at this picture, it seems hard to guess what the pattern's going to be like further to the right hand side. I mean, I had to crop off the right hand side of this evolution because the thing's growing exponentially. It would take too much computer power to to get all of the picture, and it's hard to see. But whether there's some kind of nested pattern behind this that one could derive to do with powers of 2, or I don't know, maybe powers of 3. Well, that could be the case, but it's hard to say without actually doing it. Alright, so what happens when we change the initial conditions? At the moment we're just starting with 2 red blocks. What about if we just start with 1? What changes? Well, okay, we still see this kind of complex froth being created by this thing in the middle, and the thing in the right has similar behavior. Now, let's crank up the number of red blocks. What changes? Okay, so the froth kicks in earlier, and then later, and then earlier. It seems as if this rule in the middle is quite sensitive to the initial conditions. You see, if you just draw a line at the right-hand side, that kind of is a measure of the growth rate, and it seems very, very sensitive upon the number of red blocks we're starting with. And we can also see something else fairly interesting going on in this system on the right. Let's just decrease the amount of time. So when we have 2 red blocks, see there's a little bit of interesting temporal behavior on this rule in the right, but it dies out quite fast, and then most of the complexity is kind of spatial in a way. Let's increase the number of red blocks. When we have 3, the transients lasts a bit longer. And when we have 4, when we start with 4 red blocks, it seems as if this is persisting now. You see, it looks like this complex pattern at the top here is staying on there. Although it doesn't go too deep in time, it seems to be constantly riding upon this growing string. And as we have more and more, it seems like the complicated kind of hat this rule wears is getting larger and larger. So that's kind of interesting. I'm not really sure what to make of it. I think that one of the most profitable questions one can ask of systems like this is, what is it useful for? And I'm not sure in this case, but I bet it'd be useful for something. Anyway, let's have a look at some other stuff. We'll change the number of red blocks at the initial condition back to 2. Let's just have a look at some more rules. Okay, so let's back up now. Right, so you see this rule here on the far right hand side. This is a typical example of something with exponential growth, which is essentially comprehensible. You see that although it's not exactly regular, with a bit of study, one could easily get a formula which is going to predict how the system's going to grow. Now, if we change the number of red blocks in the initial condition, it's quite robust, okay? This has a kind of what I'd call simple exponential growth. Okay, and here's a great example of, well, I suppose non-simple exponential growth. Both of these rules, well, especially let's say this one in the middle, it seems to be generating a highly complex pattern, but since the thing's growing exponentially, and since there's little going on as far as temporal dynamics, it's mostly complexity in space, I'd posit that this system in the middle here probably has some kind of underlying simple structure to it. Now, to be honest, I need to do some more mathematical analysis in these systems. to really see, because I think that the litmus test is whether it's possible for these systems to be doing computations like universal computation. Is it possible to program these kind of systems when the thing's growing exponentially? My guess is no in this particular case. And my guess is that this pattern we're seeing here is essentially a kind of ramped up fractal. It just looks complicated because it has loads of self-similar pieces, and it's difficult for our visual system to immediately see what's going on here. But this is all just conjecture, really. What about this thing on the left? Well, it looks like something pretty interesting is going on in the initial dynamics. So these are starting with 4 red blocks. Now let's change that and see what happens. Okay, so we're getting a similar kind of effect to what we saw before. When we start off with a lot of red blocks, it looks like we're getting a lot of this kind of froth on the top of the system. That's kind of interesting. So in both cases, we start off with a kind of big triangle, and it looks like, does this triangle die out? It's definitely shrinking. Yes, the triangle seems to just die out, and then across the top of it, we're getting a load of interesting complex stuff getting created. Okay, so let's now jump to somewhere different in this massive space of rules. Right, okay, so we're seeing some new stuff now. You do tend to see that systems which are close numerically, they have very similar rules, maybe just varying in one place. One kind of rewrite is different, and so they often have similar behavior. But you can change things a lot just by changing one rewrite rule. So what's going on here? Well, when we start with just 4 red blocks, we're getting linear growth in this system on the left here. But there's something else going on. There's some kind of interesting complexity growing on the right. Oops. Oversensitive mouse panel, excuse me. So what's going on here? Well, as usual, let's just increase the runtime and have a look. Right, so that was kind of unexpected. It turns out that this is going exponential. It's an interesting kind of complex growth there. Whereas this rule in the middle here is looking linear. Now let's increase the number of red blocks and see what happens. Okay, so it looks like in this case, the dynamics are very kind of robust to the number of red blocks we're putting in. Also, as far as system classification goes, there's an interesting observation. I think, what's his name? Thomas R. Borgnesi, I think his name is, pointed out when he was looking at some of these planar rewrite systems, which are network rewrite systems instead of string rewrite systems. But what he pointed out was that there were certain modes of behavior, sort of periodic, nested, whatever. And then there are other rules which seem to kind of be like hybrids, which didn't fit into any particular box. They kind of displayed elements of other previously observed behavior. So this looks kind of like what we're seeing here. This system has elements of linear, periodic, exponential growth, nested structures. It seems to kind of have it all. But in this particular case, it looks very robust to changes in the number of initial red blocks. Of course, we can set the thing off from other initial conditions, and who knows, it could do something really fancy. But for now, let's just keep with red blocks to keep things simple. So you see these systems here, these have rather high periods, and I'm guessing that these are very sensitive to the number of red blocks we start with. So with 1, let's look at this one in the middle in particular. This is starting with 3 red blocks. We get a period 1, 2, 3, 4, 5 orbits. Now we increase the number of red blocks, and the period of the orbit increases, and we start to see a kind of nested structure in the space-time pattern. It looks kind of like, if we look at successive columns, they're basically showing us what happens to particular elements in the string over time. And you can see that there's definitely some kind of nested pattern governing how long it takes these cells to change. They're changing periodically, but the period's increasing with how far you go to the right. Okay, well, let's look at something different. Oh, I clicked on that too fast. I should have stayed on it. But I presume you just saw that. That was the sort of rule which has very interesting behavior when you initialize it from lots of reds. So we found another one on the right here. Oh, actually, maybe we shouldn't talk about that one. Alright, so we've got some new kinds of behavior right here. We're starting off with 36 red blocks. And like, look at this system here. This is kind of what, on the right, this is kind of like the opposite to what we saw before. Remember before we were seeing things of exponential growth, which had a lot of complexity at the top, but, you know, at the bottom there was a kind of relatively stable looking pattern. Well, this is the same kind of thing, but switched over. Okay, so stuff like this rule on the right, I find this kind of thing very interesting. We're starting off with 36 red blocks. Then after we update, 36 blues. And then we get, I guess it's going to be what, 18 greens? And then something fairly interesting is going on. We're getting some triangles and some extra complexity getting generated. But the system's kind of ticking down. If you have a look at the rule, notice that this system doesn't actually have the ability to grow. Like, whenever a rewrite operation gets applied, it always creates less stuff than what was there before, because every one of these strings at the top, at the very top, is like no bigger than the thing underneath it, the thing that it gets replaced by. So the system has to boil down, but if we look at how it reacts to different numbers of red blocks, we get differences. So what's the width of this final fixed point? It's 1, 2, 3, 4, 5. Okay. Well, if we change the number of initial red blocks, does that change? Yes, it does. Now it's 1, 2, 3, 4, 5, 6, 7. Okay, that's with 46. With 47, it's 1, 2, 3, 4. 4 again, 48. 1, 2, 3, 4, 5, 6, 7. Interesting. So I wonder how the number of final red blocks depends upon the number we put in. So it's a kind of interesting question, I think. Let's investigate. Okay, so what I've done here is write a little code which basically just runs this system from lots of different um, numbers of initial reds. So initial number of reds is 1, 2, 3, 4, 5, etc. And we're just plotting how many reds we end up with after we've run the system for a long time. Let's increase for runtime just to make sure that we're getting the whole picture. Okay, that does make a difference. Well, I suppose one thing we ought to do just to check that we're doing things properly is make sure the system does actually go fixed. So we'll change the number of reds, and let's watch that system on the right and make sure that it always ends up fixed. Okay, so it does seem to. What about the pattern of red and blue and green blocks? Is that always the same? Well, it seems to have a similar kind of core to it at the top left, but it looks as if what goes on at the bottom right is is different every time. Well, okay, so we saw from that little experiment that it's enough to run the system for 500 time steps, and let's just concentrate on what happens for the first 50, going up to 50 red blocks. So this list here just shows us how big the final fixed point is. Is there a pattern here? Well, let's just do a list plot just to see. Interesting. Okay. It looks to me as if we've got some kind of nested pattern going on. Let's go up to 100. So the x-axis is the number of red blocks in, and the y-axis is the size of the final, presumably fixed string that we end up with. Let's join the dots. Well, hard to say, I suppose. Is there a pattern here? Can this system be used to do some kind of computation? Maybe it's like programmable matter or something. We can make it do specific things by giving it a number of initial red blocks, kind of like the way that you put code into a computer. Anyway, whatever. Let's have a look at some other systems. Right. Okay, so what we're doing here, we're starting off with, well, let's say 38 reds, and the system seems to be running down to an eventual fixed point. I'm talking about this system on the left. So it seems to run down to a final fixed point, but have a fair amount of complexity on the way. This system can't grow. If you just look at the rules, you'll notice that more material cannot be created. But the amount of apparent complexity there is here makes me think that this is the kind of system that it's difficult to know when it's gone into an orbit, when it started repeating itself, unless you actually see it literally repeat, because it's just very complicated. Let's run it for longer. So in this case, it boils down to quite a short string. This is starting with 39 red blocks. So let's change that. 40 red blocks. Pretty similar final condition, but it is different. Alright then, so let's see what else is out here for us to discover. Right, so if you look at this system on the right here, this has got another kind of behavior, something new. In particular, look at how the length of the string varies in time. What is this? Is this a periodic rule? Is it growing exponentially or linearly? Well, I think at the moment it's safe to say that the system's looks like it's in a kind of transient state. I'd guess if you let the system run long enough, it's going to end up periodic, maybe period 1. But ultimately, it's difficult to know. It could be that if the system runs for long enough, something snaps into place and the system starts growing exponentially. You do see things like that. So ultimately, I'd say that all we know for sure about this system on the far right is that we don't know what it's going to do for sure. Another very interesting and rare thing that we're seeing here is that the system, if we just look at the left-hand side or near to the left-hand side, it's not repeating with a very low period. Like almost all of these rewrite systems, if you look at what's going on at the extreme left, it's very, very fast repeating. But here it isn't. I'm not really sure what that means, but I think it has something to do with the system being less predictable. Anyway, I'm fairly interested to see how this system pans out, so let's increase the runtime. Okay, so we double the runtime, and we still don't really have any clear idea what's going on. The system hasn't started repeating itself yet, although it does look as if it's very, very slowly getting smaller. But of course, these kind of rewrite systems, they can double in size with the click of a finger if the right things are happening inside. So we double the runtime again. Okay, it's just getting smaller and smaller very slowly. So in this case, I'm guessing it's going to end up with a very, very small string, which is periodically repeating. Just a guess. What happens if we change the number of red blocks in the initial condition? Are we going to see some other kinds of behavior exhibited? So this is with 45 red blocks. What about 46? Okay, it seems to be dying faster in this case. 47. Very similar in that case. 48. Wildly different. Okay, this is one of those hard to understand rules. Let's move on. Wow. Okay. So this is pretty wild. The system seems to die. I'm talking about the thing on the right, if you hadn't guessed. The system seems to die off. At least it grows out a large string of. Is it just a repeating string of red and blue blocks? Let's magnify this. Not very dexterous this evening. Okay, so it seems to generate this large string of red and blue blocks with a tiny amount of three-color fluff on the right-hand side. And then this thing seems to die off at a linear rate, while all of this kind of froth on the right seems to be kind of self-replicating or something. What's interesting, I think, particularly, is that this as this thing dies off linearly, some sort of exponential growth seems to kick in on the right-hand side. So, yeah, I think that's fairly interesting. I wonder what happens with other initial conditions. I'd guess that this is the kind of system which can grow exponentially, but only if there's over a certain threshold of the number of red blocks that we begin with. So this is with 48. What's about with 13 red blocks? Oh no, it's still doing the same thing. It's just doing it in a different way. Right, and if we start with no red blocks, or 3 anyway, the system still ends up growing big, but it doesn't end up doing that whole kind of making an ordered pattern and then destroying it at the beginning behavior. So it looks like it's the order which is the transient bit, and the bit that requires a lot of reds to kick off. Right, let's have a look at some other systems. Okay. So it looks like this one here, this is something you don't see very much. It seems to be producing these patterns which are quite complicated in a kind of zoomed in way. Like these lines of red, blue, and green are fairly intricate, considering that they're all generated by just starting with 3 red blocks. But there's only really a very finite amount of information here. I mean, I don't think it would take long to write down a formula for exactly how this particular instance of the thing is running. What about if we change the number of reds? Okay, so we're just changing the form of these kind of trails which seem to be generated. Doesn't look like we're making anything fundamentally different really happen with the intrinsic dynamics from a subjective point of view. Right, so let's move on. I think we've had a look at most of the kind of behavior that these systems display. I mean, you can always find outliers which will surprise you, and that's why looking at these systems is so entertaining. And I think that one of the most exciting things to look at in these systems is trying to find applications. So one thing I was looking at in the paper I wrote on these things is how you can perform multiplication. So you start with a number of red blocks, say 5, and you look for something which multiplies that by 2. So it ends up generating something which grows and then ends up stopping, so that it ends up generating a fixed string with twice the length of the initial string. And you can look for things like that, which effectively perform arithmetic. But no doubt, there's a lot more interesting things you can find. One of the issues is to design a search which will find you that thing. So I imagine there's string classification, well, rules which essentially classify strings. So if the initial string contains a blue block, then it'll die out. If it doesn't, it'll end up at some fixed pattern or something. No doubt there are systems like that which can be used for classification. One of the difficulties is to design a kind of procedure that can allow you to go fishing for these kind of systems. Okay, so let's wind things up now. We can wind up with this particular system here. So we're starting off with 7 red blocks, and look what's going on. I mean, it's easy once you've seen like several thousand of these rules as I have to get quite kind of blasé to it. Oh yes, it's just another system with complex growth. But I mean, if you can really step back and kind of remember how it is to see a system like this through fresh eyes, it's really remarkable. We just start with 7 red blocks and these tiny rules. And where does all this complexity come from? Is it just encoded in the initial rules? Are we just seeing some kind of pre-programmed platonic forms or something which this thing is tapping into? I mean, it just, that surprise factor of all of this immense amount of information being somehow contained within these rules is something which I think is still quite wonderful. Um, anyway, I encourage you to look at these systems. If you found this video interesting, then why be a spectator? You can go to the website where I have a system like this which will run in your browser and have a look for yourself. Try some different initial conditions. Try and find some applications. Um, and I mean, get in touch if you want to work on this kind of stuff, because I think that there is a lot of potential for finding applications in these systems.